Hello and welcome again. In the previous video, we talked about this example here, which is multiply this polynomial times this polynomial in the Galois field of 2 to the 8. Now, we actually got the answer, and the answer, the way we got it was we just multiplied them, and then we divided by the polynomial p, which is this one right here. So this is the polynomial p we divided by. So we took this polynomial, which remember represent this byte over here, and this other polynomial, which represent this byte, and then multiplied them. And if you remember what we did last time, when we multiplied the polynomials that we have here, x to the 5th plus x cubed times x to the 7th plus x, which are these two polynomials, this one and this one, we got this answer. And the way we got this answer to reduce to a polynomial of degree 7, so we can now make this an element of the Galois field, is we divide it by this polynomial p. So we do the long division of polynomials. That's what we did last time. Now, what we're going to do now in this video is we're going to arrive exactly to the same answer, but we're not going to do long division. This is another way to do it. The other way to do it is this. Because we're dividing by this polynomial, basically when you do the remainder of the division, what you're actually doing is you actually replacing anything that has a power that is x to the 8th, you replace it by x to the 4 plus x cubed plus x plus 1, which is x to the 8th will be identified with this here modulo the p of x. That's basically what's happening. Now, if you don't understand what that means, it doesn't matter. It's an algebraic construct that you can actually do. So when you mod by this polynomial, or when you do the remainder of the polynomial, what you're really doing is you are kind of identifying x to the 8th with this other part of the polynomial. So you identify this polynomial with this part. And that's going to allow us to reduce this to degree 7 or less. Now, so you do exactly the same as before. You take the polynomial that is here, multiply by this one, the same way you do polynomials, multiplication, and if there is some like terms, you have to add the coefficients, but you have to add them with XOR, X-O-R. And so we do arrive to this answer. So I'm not going to do it again because we did it in the last example. If you don't remember, go back and watch that video to see how this polynomial is actually the answer of this multiplication, this one by this one. So we got this. So what we need to do is reduce the degree of this polynomial by dividing by p. And this is the other way to do it. So in here, I have some powers which give no trouble, which is x to the 6th and x to the 4. These powers are okay because they are degree less than 7. Now, the powers that are not okay is this x to the 12 and x to the 10. So I'm going to mark those down, and I have to reduce those powers. So I'm going to reduce x to the 12 and x to the 10 there. So how am I going to do that? So let's start with the x to the 12. So the x to the 12 power. And let's reduce that power. So I have x to the 12. Let me use the white color here. So I have x to the 12. And I want to reduce that. Now, the way you're going to do it is you're going to break this power, break it down into a product in such a way that x to the 8 appears in that product. So how can we do that? What is x to the 12 in terms of x to the 8? I can write it down like this. I can write it down as x to the 8 times x to the 4. And the reason for that is because of the loss exponents. If you take an 8 and add it to 4, you get a 12. So this is the multiplication. Now, how do you find out what these powers are? What you do is just take the power. If the power is bigger than 8, you just write it down as x to the 8 times whatever x you need to make it go up to this degree. So if I put an x to the 8 here, I know I have to put a 4. So it can go up to x to the 12. So that's how you do it. Now, the way you're going to reduce that is instead of looking at x to the 8th, like a power x to the 8, we're going to identify x to the 8 with this whole polynomial that is here, x to the 4 plus x cubed plus x plus 1. So I'm going to kind of replace it over there. So let's say x to the 4 plus x cubed plus x plus 1, and I'm going to multiply by x to the 4th. All right. And so let me go back again. So we did x to the 8 times x to the 4, which gives me x to the 12 because I have to reduce this power here. And what I do is I replace the x to the 8th power by this guy here. Why? Because it's kind of saying that this power is exactly the same as this one over here. All that. Alright, so what we're gonna do now is just do multiplication of polynomials again. So let's see what this one is equal to. So I'm gonna multiply the powers. So I'm gonna multiply x to the 4 times x to the 4, x cubed, x, and 1. So you just basically you're gonna use the distributive law there for multiplication. So you're gonna multiply by x to the 4 times x to the 4 here, x to the 4 times x cubed times x and times 1. So let's do that multiplication here. X to the 4 times x to the 4 gives me x to the 8th power, plus x to the 4 times x cubed gives me x to the 7th power, plus x to the 4th multiplied by x gives me x to the 5th power, and x to the 4 times 1 gives me x to the 4th power. Alright. Did I reduce the degree of the polynomial? Yes, I reduced x to the 12, but I still have an x to the 8 here. So you don't want that. You don't want x to the 8th to appear there. So every time you see an x to the 8 there, just replace it by x to the 4 plus x cubed plus x plus 1. So I'm going to replace this guy right here, x to the 8, again, by this other polynomial here. So I'm going to write it down over there. So that's going to be equal to x to the 4th plus x cubed plus x plus 1. That's the x to the 8. And of course, I have to still write down the rest. I have to write down x to the 7 plus x to the 5th plus x to the 4th. Right? And you have to simplify if you had like terms. In this case, we have a like term. X to the 4th is a like term. So it's here and it's here. Because of that, because I'm adding x to the 4 plus x to the 4, remember that is going to be 0, x to the 4, because the addition here is done with sword. So basically what I'm doing here is canceling out this x to the 4. Okay. Now this doesn't make sense in college algebra, but it does make sense here in the Galois group. Okay. So this is the addition in the Galois group, not the polynomials. So now that I look at that, I don't have any more like terms here. So what I'm going to do is I'm going to write down this polynomial here that is left, and I'm going to organize that power in decreasing order of powers. So I'm going to write down the x to the 7th first. I'm going to write down x to the 7th plus x to the 5th is the next power, plus x cubed plus x, and then plus 1. That polynomial that I just wrote down over there is this one that is right here, but just organized in decreasing order. So basically what I'm saying is that x to the 12 is equal to that polynomial that is over there. Now this does occur again. This doesn't make sense in college algebra, but it does make sense in the Galois group. Okay, so I'm gonna mark that down with. Let me use a color here. So let's say this one. This is x to the 12. So I achieved that goal. The goal was to reduce the power x to the 12 to something that is a power 7 or less, and I achieved that. X to the 12 is this polynomial of degree 7 or less. Okay, so that's what we have so far. Now, I also have to do that for the other power, which is x to the 10 power. I also have to do that. So let's do x to the 10 power. Same idea as we did with the x to the 12. So let's take x to the 10 power, and I'm going to write it down in such a way that I have an x to the 8 times another power x. Now, to complete the 10, of course, I have to have a 2, so that's going to be x to the 8 times 2. And again, I'm using the rules of exponent. And I'm going to do exactly the same thing. Instead of using x to the 8th here, I'm going to use this polynomial here, x to the 4 plus x cubed plus x plus 1. So I'm going to write it down over there. So I'm going to say x to the 4th plus x cubed plus x plus 1, and that is multiplied by x squared. All right, so what do we have now? So what we have now is we need to reduce that x to the 10, right? So multiply it out. So I'm going to take the x squared and multiply by x to the 4, x cubed plus x plus 1. So I'm going to go a little bit faster here. X squared times x to the 4 is x to the 6 plus x to the 5th plus x cubed plus x squared. And I don't have to do any reductions anymore because this polynomial is already of degree 7 or less. So what I'm saying here is that x to the 10th, let me use the color here, x to the 10th is that polynomial. Again, this doesn't make sense in college algebra, but it does make sense in the Galois group. Okay. So that's what we have so far. So we have reduced x to the 12 and x to the 10. We reduce it to the polynomials of degree less than 7. Now, what we're going to do is, let me call this one 1. Let me call this equation number 1. And let me call this equation number 2. What I have to do right now, and this is the final part of the process. What I have to do right now is replace x to the 12 by the polynomial which I just found, replace x to the 10 by the polynomial I just found, and add x to the 6 and x to the 4th, right? So let's do that. So I'm going to do that, and that would be the answer after you, of course, simplify the whole thing. So let's do that. So what I have to do is, let me erase this part over here. Okay, so I'm going to write down that polynomial. Right? Remember the polynomial, the answer of the original multiplication is all the way up here. So this is this one right here. So it's x to the 12 plus x to the 10 plus x to the 6 plus x to the 4. So let me write it down again. This is x to the 12, x to the 12 plus x to the 10 plus x to the 6 plus x to the 4. And I'm going to replace the x to the 12 and the x to the 10 by the values 1 and 2. So here I'm going to use the equation 1, replace it, and I'm going to use the equation 2 for this guy right here. So what is equation 1? Equation 1 says that x to the 12 is this guy right here. So I'm going to just write that down. So I have, let me see here, with color. So I have x to the 7 plus x to the 5th plus x cubed plus x plus 1. That would be x to the 12. That again, that is right here. Is this one. And then I'm going to add x to the 10. But x to the 10 is this guy right here. So it's going to be plus. Let me write it down here. So plus x to the 6 plus x to the 5th plus x cubed plus x squared. And finally, I have to add the last two parts here, which is x to the 6 and x to the 4. So plus x to the 6 and x to the 4. I just realized that I did this all in diagonal, but it's okay. All right, so what we need to do here is, of course, I need to simplify. So I need to collect all the like terms that you see here. Okay, so I have an x to the 7. So x to the 7 doesn't have any like terms there, so it's going to be just x to the 7. Let's see x to the 6. Let me mark down the x to the 6. So I have an x to the 6 over here. And I also have another x to the 6 over here. That is addition. I have to add those. And remember, the addition here is sort. So x to the 6 plus x to the 6 will actually cancel out. And so I won't have an x to the 6. Okay, do I have an x to the 5th? Let's see. Let's use another color here. I have an x to the 5th right here with that green color. And I also have another x to the 5th over here, and I don't have any more x to the 5th. And because the addition is sort addition, that addition x to the 5th plus x to the 5th is gone. Do I have an x to the 4th? Yes, I do. I have an x to the 4 right here, but it doesn't combine with anything, so it's going to be plus x to the 4th. And I'm done with the x to the 4. Now, do I have an x cubed there? Yes, I do. I have an x cubed. Let me use another color here. I have an x cubed right here with the yellow one. And I have another x cubed right here. Because it's addition with sort, again, they cancel out, so I don't have an x cubed at all. Do I have an x squared? Let's see. Yes, it is right here. I'm marking down with yellow over here. I have an x squared. But it doesn't combine with anything, so it's going to be plus x squared. And I'm done with the x squares. Do I have an x in here? Let's see. I have an x over here. And so what that does give me, that's going to give me x only. And plus 1. So as you can see here, we get the answer there. We get the answer. Now this answer that we have here is exactly the same answer we get for the previous way to do it. So we get the same answer whether you do it with division of polynomials or whether you do it this way. So which one is the best one? Well, that depends on you. Which one is easier for you? Whatever this is easier for you, that's the way you do it. I don't mind doing one or the other. I personally think that maybe the division of polynomials might be a little bit more algorithmic. This is kind of like you have to try to break down things in a certain way. Now, I like both of them. Both of them are okay. So whether you use one or the other really depends on whether you like one over the other one better or which one is the easier for you. So that's how you do the multiplication of polynomials in the Galois field. Now, this doesn't hold true, of course, for normal polynomials. But when you're talking about normal polynomials here, these are not normal polynomials. These are polynomials in the Galois field, which behave in this way. So that's actually all I have to say about now. Now, if you want to write down what is the byte that this one represents, you can go ahead and just write it down. So it's going to be 1, 1, 1, 0, 1, 0, 0, 1. It's going to give you exactly the same as the other one. So that's all for this multiplication. So those are the key parts that we need for the mixed column. And what we will see in the next video is how we're going to use these operations to transform the bytes that we have after we did the shift rows. So I will see you in the next video.